Hi everyone. This is Abha from NGIT. So I'll be hosting this in this seminar today. So I would like to welcome you all in the 17th seminar in the Indus seminar series. So today our speaker is Mr. Soumyaranjan Khuntia. He's a PhD researcher at Indian Institute of Astrophysics. So he'll be talking about heating versus cooling in CMEs, the thermal history of fast and slow events across um, solar distances. So before he starts, I would like to introduce him a bit. Like he's a fifth year PhD student, currently pursuing his PhD under Dr. Vagish Mishra, and he's preparing his PhD synopsis soon. He holds a MSc physics degree in the specialization with the theoretical physics from Indian Institute of Technology, Delhi. His PhD research focuses on the kinematics and thermodynamics of solar coronal mass ejections. So there are number of things like he is currently actively participating in the science outreach, and he's a senior editor with the Dude magazine. So I cannot add up all here, but yes, I would like to start this seminar. Is that okay, Soumya Ranjan? Can I
Yes,
do
yeah.
this? Come on. Okay. So since you opted for the interactive session, so questions will be in between. So be prepared for that, and people can ask you in between. Okay. So the time, like it's like 1 hour. So you can end up before that as well. So over to you. Yeah.
Yeah. Thanks, Ava, for this introduction. And a big thanks to the Indus team for giving this platform. I think I'm audible, right?
Yes, you are audible.
Yeah. Okay, yeah. So, yeah, big thanks to the Indus team for giving this platform. And I'm glad to interact and discuss my work in this platform. So, in this present seminar, I will give you all uh, a comprehensive overview of the thermal history of coronal mass ejections when they're propagating in the interplanetary space. So I'll start with like what is a coronal mass ejection. So these are simple, large-scale eruptions of magnetized plasma from the solar corona into the heliosphere, and once they erupt from the solar corona, they propagate in the interplanetary space, and they can come, in and interact with the Earth atmosphere as well. And these coronal mass ejections, these transient events, are fast observationally detected by, also 7 spacecraft. And these structures, like we are being in this coronographic movie, you can see in the left side, or you can see my cursor, I think. Yeah. And the right side image is the LASCO C2 field of views. This is one of the spacecraft that is viewing the sun, the corona, the solar corona, in different field of views. And these structures, these bright structures that you are seeing here, is like the density structures. And these are like we can see them just because of the Thomson scattering of the photospheric white light. And this is a classic three-part structure of a CME, that CME consisting of a bright leading edge, then followed by a dark cavity, and this is the high magnetic field region of the CME, and it followed by a bright core. And just to give a context that these are the some characteristics of a CME, that the mass is ranging 10 to the power 12 gram to 10 to the power 16 gram, the speed some few 100 kilometer to few thousand kilometer per second, and there is a good correlation of the occurrence of CMEs with the solar cycle variation, and the temperatures of the CME can vary, near the sun up to 10 to the power 6 and up to near Earth around 10 to the power 4 or 5 Kelvin. And the motivation to join my PhD also uh, come to, I did my PhD just because of the seeing by the practical importance of the CMEs. So when the CME come to Earth, they can cause a beautiful aurora. At the same time, they can cause various disruptions in our near Earth space. Because these are ultimately these are like energized plasma particles. So then when they hit our atmosphere or any conductor, they can induce huge amount of current. So they can interrupt, let's say, the satellite or the near Earth satellites, or they can cause disturbance in the radio waves or navigation system or telecommunication systems. So these are some of the practical importance that when the CME hit Earth, they can cause various disturbances in the near Earth space. So, so, but the kinematics of the CME is well studied, but the thermodynamics of CME is not that much studied, or you can say the study is very limited, just because we have some observation limitations for the CME cases. So I have categorized like three type of observations that we have now, like widely used for the CME cases. So one is the extreme ultraviolet imaging or spectroscopy, and the second one is the white light coronagraph, and the third one is the in situ observations. So each of these observations have their limitations. So the extreme ultraviolet imaging telescopes, or the spectroscopy or imaging observations of the CME, so they give you better details about the CME structures and the internal structures or any kind of Doppler shift or the plasma motion, and also give you detail about the temperature or the density information about the CME plasma. But these have a restricted field of view that you can do the spectroscopy or extreme ultraviolet imaging observation near the sun. And in the white light observation that widely used, these have a very wide field of view that you can see from 2 to 3 solar radii up to 1 AU or beyond 1 AU. Also, you can track a CME, so that you can know better the kinematics of the CME in the white light coronagraphic observations. But as I told before, these observations are simply just a scattering of photospheric light, so they lack the internal plasma information. And in the last one, the in situ observations. So here, the spacecraft like PSP, Solar Orbiter, or WIND, Messenger. So they when the CME propagate in the interplanetary space and spacecraft come across it, the spacecraft directly measure the plasma parameters like temperature, pressure, density, etc. And they give a better detail about the plasma, but but we have at certain heliocentric distances these in situ spacecrafts. So there is not a wide coverage from near the sun up to, let's say, 1 A. So there is a sparse distribution of in situ spacecraft. So that's why we don't have any continuous plasma measurements from near the sun up to or at least 1 A. So that's what limit our study related to the CMEs. And as I told, the CMEs have a practical importance. So similar to our, in our Earth, similar to our weather forecast, like related to rain or cyclone, we something called we have like a space weather forecast. And the space weather forecast has two main ingredients. One is the arrival time of those transient structures, and the second one is the geoeffectiveness of those transient structures. And the arrival time of the CME that we can better predict, simple using the kinematics of the CME, let's say the propagation, the expansion of the CMEs. But for the geoeffectiveness, like to know the impact of the CME on the Earth atmosphere, we need the kinematics of the CME as well as the plasma information like magnetic field, or the direction, the pressure, temperature, density, etc. But as I told before, like the observation point of view, we have something called the global informations, like from from the white light coronagraphic observation, we can get to know about the overall global shape of the CME or the global kinematics of the CME to some extent. But the local information, such as, let's say, the in situ spacecraft, or how the plasma properties vary across the CMEs, we don't have that information yet. And also, as the in-situ spacecrafts are at various local heliocentric distances, we only know about the local plasma properties. And to connect that local plasma property to the global characteristic of a CME is very challenging. And in addition to that, when the CMEs are launched and in a successive manner, like at a small time window, those CMEs can interact in the interplanetary space. and they can further put some challenges to know their arrival time and their geoeffectiveness. And for that, during my PhD, our one of the focus is to overcome these challenges and try to know how, how to connect those local information to the global information, so that we can try to better understand the arrival time or the geoeffectiveness, and try to contribute something to the space of the forecast. And for that, our main consideration is that the CME, the internal thermodynamics, can govern the global kinematics, and the global kinematics also can have some impact on the internal thermodynamics. So, here, because from the global information, like let's say the white light chronographic images, we can better know the global kinematics, so that we try to know, from global kinematics, can we derive the internal thermodynamics, so that we can know the trend, at least, where there is no observation available yet, so that we can try to know how the internal thermodynamics, like the temperature, the polytropic index, the thermal state of the CM is varying across various solar distances. So our main focus was to connect those kinematic information, the global information, and try to derive the global plasma information, like the whole, what is the temperature of the whole CME plasma, how it is evolving with time or with distance. And as because in this modern era, we have like PSP and let's say the Parker Solar Solar Orbiter, and many other in situ spacecraft in between Sun and Earth, so that we can use those local information and our model derived parameters, so that we can better understand the kinematics and the thermodynamics of the CMH. And for this seminar or this talk, I'll try to give you only two overview, like near the Sun, what is the thermal state properties, and near the Earth, what is the thermal state properties of the Sun, the CME. So as I told, like we don't have any thermodynamic observation available in those heights, like say after 3 solar radii. So for that, we have developed a model called the Flux Rope Internal State model. So this model was first developed by Wang et al. In 2009, then further rectified by Mitra et al. In 2018. Further, during my PhD, I also modified this model, and so this is a view of the model that the model consider in a local scale, because when the CME travels and reached Earth, the radius of the CME itself is more than 50 solar radius. So in a local scale, we consider the CME as an axicylindrical symmetric flux rope, and we consider three motion of the CME plasma, that is the propagation, and the second one is the expansion of the CME, and the third one is the polarial motion of the CME. Polarial motion is the plasmas are moving along the axis of the CME, around the axis of the CME, and we consider three forces that are responsible for the expansion of the CME: the Lorentz force, the thermal pressure force, and the third one is the centrifugal force. And also we consider that in our model that the CME is propagating in a self-similar manner. And yeah, here I will give you a sneak peek of the FRIS model. That this is the flow model. We consider in the model the conservation of mass, angular momentum. Then we solve the imaged equation for the single magnetic fluid. Then we apply the law of thermodynamics, polytropic process. Then we solve the radial equation of motion and try to estimate the internal thermodynamic parameter of the whole CME flux loop. And these are the consideration of model. And one of the major consideration is that we consider the CME is propagating, the processes inside the CME when the CME is propagating is a polytropic process. So this is a general process compared to any other thermodynamic process that we have heard of, that let's say, isothermal process, adiabatic process, or isobaric processes. So here you can see this PV to the power gamma. So this is the capital gamma. So gamma equal to constant. So in general, what happened, like in imaged simulations, people put this gamma value as a constant value, the adiabatic index 5/3. But here in our model, we keep it as a free parameter that it depends on time, so that any variation in gamma with time, we can get to know about the thermal state of the CME. That if the CME has a gamma value less than this adiabatic index, that is 5/3, that means there is an injection of heat, or the CME is producing heat. So that means the system is now heated. And if for the CME plasma has a polytropic index above this 5/3 value, that means there is a release of heat, and which is also natural. because CME is expanding and as well as propagating. And we try to solve this equation of motion for the plasma that particularly we solve this radial equation of motion. And here we try to connect this P to this polytropic process so that we can connect the kinematics and the thermodynamics of the sea. And these are the parameters that we can derive from the FRIS model. So these three forces: Lorentz force, thermal pressure force, centrifugal force, and all other like thermal parameters, the density, pressure, temperature, and the rate of change of entropy, heating rate, and polytropic index. And as you can see, all those parameters are now, if you see this third column, the value one, and here all those parameters now defined in terms of the kinematic parameter, that is the radius of the CME or the height of the CME. And the unknowns are like C2, C3, C1. These are the unknown parameters, and these are some factors. So that now we can derive, now we can convert every thermodynamic parameter uh, and try to connect all those to the kinematic parameter. And the kinematic parameter, because CMEs are 3D objects, they are propagating in a real 3D space, and we are taking only a, a two-dimensional image, so they suffer projection effect. And to mitigate that projection effect, we have to use some sort of 3D reconstruction method. And for my work, I have used the graduated cylindrical cell model to derive the 3D kinematics.
Shomo,
And for
hello. Hi. Hello.
uh, yes,
Hello.
yeah, hi,
Yeah, you can
hello,
hear me? Yeah, so I
yes.
just want to ask you, what is this lambda, the small lambda?
Yeah, so this is like also again an unknown parameter. Like it is a combination of some C1, C2, C3, like a combination parameter. Like it's just we term it as the lambda. Like it is a combination of C2, C3, C4.
Okay,
Like
so it's a function of length,
some
radius, time, and a lot of other things, right?
yeah, yes, yes, yeah,
Okay. Yeah, thanks.
yeah. And if you can see here, like these K2, Ks, because ultimately, in our model, because all those parameters that we are deriving, you don't have any observational constraint there, right? So we cannot, uh, in our model, whatever parameter we are deriving, you can say, let's say, temperature. So temperature is now a function of lambda, also a function of some unknown factor, that is K2, K8 by K4. And in our model, we try to solve for these unknown constants like C1, C2, C3, C4, and we try to, get a value for that. But these factors are, they have a degenerate value, like, we can assign multiple values. So these factors can be constrained once we, try to verify our model derived results with any in situ parameters, like direct observations. Let's say we derive some temperature from in situ measurements and cross verify with our temperature, model derived temperature, and then we can set this factor. But for now, like these factors are unknown to us. And for this seminar, I'll try to only focus on two properties, like the polytropic index and the temperature profile of all the CMEs. So, like once we derive this model, the FRIS model, we try to apply into two CMEs. One is the fast CME, one is a very slow CME. The idea is that if we focus on two different class of CMEs, and let's try to see if the thermal state of a CME or the temperature CME is vary so much or not, or they are similar kind of. So in the fast CMEs, the CME has a speed around above 1500 kilometer per second, and also it's not dropping that much. The acceleration profile, if you see the third panel, it shows a rapid deceleration in the initial heights, and thereafter at a higher heights it maintain a near constant acceleration profile. And for the slow CME case, we found that the CME is gradually increasing its acceleration, and the speed is also, if you see, it's around 100 kilometer per second near the earth, near the sun, and it rise up to some 450 kilometer per second at around 15 solar radians. And these are the model derived polytropic index for the fast CME in the left panel, and the right panel for the slow CME case. And if you see the polytropic index for the fast CME, So for the initial heights, we see a polytropic index value greater than the 5 by 3 value. If you see this green color line, this is the 5 by 3, that adiabatic index. So as I told, like if a polytropic index value is above this adiabatic value, that means there is a release of heat, and below this value means there is an injection of heat, or the CME is getting heated. So as initially, the CMEs have a inherently high temperature. So once they and also in near the sun, they expanded too much. So that's natural that they will show a heat release state in the beginning of their journey, and soon after certain height, let's say for the first CME, it's around some 3.5 solar radii, it will transition into a heat injection state, and then thereafter it maintain a constant polytropic index value around a value of 1. So 1 means that PV to the power 1 equal to constant. That means it's a isothermal state. And for the slow CME, we get a similar kind of a trend for the polytropic index. But here, the polytropic index decreases very gradually, like not fast as the fast CMEs. And here it gradually drop, and again it maintain a polytropic index value of 1 at high heights. And here we call the transition height as the turning height of heating, the THH. And we see that for the fast CME, the turning height of heating is around 3.5 solar radii, but for the slow CME is around 5.5 solar radii. That means the fast CME try to come into a heating state very early compared to the slow CME.
Hey, Soumyaranjan, Kalpesh here. Hello, am I
Yes, hi.
audible?
Yeah,
Yeah.
Kalpesh.
I just want to ask, means if you see here, if you see in your fast CME analysis,
Yeah.
there are less number of data points are there between typically your, I think two RE, means two solar radii to I think this, and it's
Yes,
similar
yes.
in the low solar ICME case. The data points are means there are significant data points during that transition region. So how are you means I don't know how what's your basis to say that means this is fast means this is sudden drop and this is gradual drop.
Yeah, if we can see, like, can you see my cursor, right?
Yeah,
So
yes,
if you
yes.
see, like from this point to this point, so this is like, I think, 5 minute cadence data point. This is, I think, core 1 data point. So you can see
Yeah,
from here to here, this is a 5 minute data, and there is a sudden drop from here to here, right? So this transition is,
yeah.
I'm saying this transition is sharp, but here for this CME, obviously we don't have this data. So I'm not saying
Okay.
about the transition is sharp or not, but here, like from here to here, this transition, like from, let's say, crossing this adiabatic value to reaching isothermal state, this trend is very gradual compared to this one. Here it will directly come to isothermal state, and then
And
again,
I'm
here
just
for.
curious, if these are the
Mhm.
model derived, then here you have the you have observations till 20 solar radii, and here you are restricted till 16. And how is it? I don't know. Means,
Because for as I told, like for my model, I need the input, the kinematics as the input, right? So
hmm,
for the slow CME, whatever the CME we choose here, I think 2018 CME. So here, what happened? Like the CME is very faint, and at core to field of view, even it is very faint to see, like to track that CME. So at 14, 15 solar radii is very faint. So we get lot of error in our kinematics. So that's why I didn't include after this 15 solar radii. And for the fast CME in general, because fast CMEs are very they looks good up to higher heights also. So that's why I track that CME up to higher heights from the solar area. And
okay.
like you can apply to any CME, any height, as long
Hmm,
as you have the kinematics for them.
okay. Thank you.
Okay. Yeah. So now what we did that we try to know the source region, the source information of these two CMEs. And for the fast CMEs, if you can see that. So we see, in the multivalent study from AIA and this HMI magnetic field region. And after that, in overall, we found that the CME is associated with the flare and that active region flare. And we did a DM analysis. So DM analysis, it tried to know the temperature of the plasma. And we first try to figure out, what is the flux rope of the CME, because when the CME erupted, it is associated with the flux rope. Like the CME itself is a flux rope. In the near the sun, you can try to find the flux rope, and we try to do the TDM analysis, and from there we get to know the CME is associated with the hot flux rope. So this is just a fancy name of a flux rope. The flux rope has a temperature of 8 to 15 million Kelvin temperature, and these are the electron temperatures. So we expect that, if the background coronal temperature is let's say 1 to 2 million Kelvin temperature, and the CME flux rope has itself 8 to 15 million Kelvin temperature, so there is a potential heat release state for the CME near the sun. And also, as the CME is expanding, not for my CME, like for this CME, we couldn't track it to, let's say, 1 or 1.5 or 2 solar radii below that. Because at that height itself, statistically people find out that, in those near the sun heights, like 1.5 or 2 solar radii, people, the CMEs try to expand too much, and thereafter it decreases and maintain a constant acceleration profile for in general for the CMEs. So we expect that, because of this hot flux rope and because of the rapid expansion of the CME, the fast CME shows a heat release state near the sun. And for the slow CME case, this is a CME associated with the filament eruption. And so that's why we couldn't do the DM analysis for here. But by seeing, because the filaments are generally cooler compared to the coronal temperature. And so that's why, like, we expect maybe this CME may not be that much hard to release heat, but we couldn't get a confirmed idea from this near the sun observations. Then what do we read that, because the fast CME shows a clear trend from heat release state to a heat injection state. So we try to apply these FRIS model to various CMEs, like various fast CMEs. So here the fast CMEs means, like, simply we put a criteria, the speed is above 450 km per second. But if you see, the left panel is the leading edge speed, and the right panel is the leading edge acceleration. So all those CMEs are fast CMEs, but the trend in the kinematics is very different. That some CMEs are decelerating, some CMEs are slowly accelerating, and some CMEs are let's say have a negative acceleration, some CMEs are positive acceleration. So there'll be different kinematic profile. So here the question that we asked that, are there some difference or similarity among all the events from their internal plasma evolution perspective, because these are all fast CMEs and with a different kinematic profile. And I'll try to sum up all those the results in a schematic fashion. So here the x-axis is the heliocentric height, and the y-axis is the polytropic index. And as the CME propagate, it gets bigger and bigger. And one of the threshold I gave with adiabatic state, and another is isothermal state. So when the CME propagate, the polytropic index initially, like we found for all the fast CMEs, that there is a rise, then there is a, they get attain a maximum value. Then after that, there is a transition, this increasing, then decreasing, then it will transition this adiabatic state. Then it again goes to isothermal state, below isothermal state even, and then it maintain isothermal state at high heights. So the initial, this state, like there is a heat release state initially found. And this we state that rapid decrease in temperature and pressure also we found here. And the polytropic index is obviously above 1.66 value. And this turning rate of heating for all the fast CMEs, we try to find out, and it comes around 3 to 7 solar radii. So within that height, all the CME try to transition into a heat release state to a heat injection state. And thereafter, at higher heights, the polytropic index stays near a value of 1, that is isothermal state. And there is a moderate decrease in temperature, and also moderate decrease in pressure also that height. But near the sun, there is a rapid decrease in temperature, rapid decrease in pressure and temperature also. And for that, for all the CMEs, again, we did DM analysis because all our fast CMEs, they associate with the flare eruptions, and so that you can, see the flux rope very clearly in the solar corona. So we try to find did a DM analysis and try to find out the temperature, and we find out that all the CMEs again associate with the hot flux rope, and the temperature again is 3 to 8 million Kelvin temperature. So there is a probable heat release state at the lower coronal heights. And then what we did that, because the CMEs, when they when they propagate and reach that Earth, so in general we have that idea that when the CME has a negative BZ component, uh, cause geomagnetic storm, and higher the BG value, it will cause more the strength of the geomagnetic storm will be higher. But it's if you see, in general, that higher BG will not give a one-to-one corresponding to the higher DST value or something. So that means that it's not only about the PG, maybe the temperature, the pressure, the density of the CME also matter to cause a bigger geomagnetic storm. And also, as I told before, that the successive CMEs also put a constraint to know the evolution of the CME, the thermodynamic evolution of CME, and also the kinematic evolution of the CME. So what we did that in our next work, that we tried to know how the successive CMEs behave, how the thermodynamics of successive CME evolve with the time, and around that time this May event happened. So to give a context, that these are the sum of the events that happened previously because of the geomagnetic storm, and they cause uh, some disruptions in the near Earth space, and also in our near in the ground level also. And in recently this Starlink satellite event happened, that in February, I think February 2022, that almost around 38 SpaceX Starlink satellite get deorbit after their launch. And if you see, the DST index is not even that much high that time. So that means there is some connection to the plasma of the CME, maybe temperature, maybe pressure, or something else. And interesting, this plot I got, this is some Parker 2024 paper. So here I found, our reliance on the payloads that we have launched nowadays. So this is, I don't know why they gave a sunspot number here background, but this black one shows the number of payload launched per year. So you can see recently, like after 2018 or 19, these payload launches are exponentially increasing now. So it shows that our dependence on the technology driven any let's say satellite or anything, like we now solely depend on the technologies. So and depending on the considering the past events like these big events, it uh, is crucial that the storms happened before and also will happen again and again. And the basic idea is to understand those storms and advance our technology so that we can mitigate some of the effects of all those CMEs. And to give context, that geomagnetic storms are simple as a major disturbance on the Earth magnetosphere that occurs when there is an efficient exchange of energy from the solar wind into the near Earth space. And this solar wind can be maybe the cause maybe a CME, that the coronal mass ejection, or maybe a co-rotating interaction region. And the CMEs are measured in terms of various indices. One of the indices is the disturbance storm time index, or shortly we called DST index. So these are simple, measurement of magnetic horizontal component of Earth's magnetic field at various equatorial regions. And this is a typical profile of a geomagnetic storm. So there is a decrease in Earth horizontal component of magnetic field. So there is a negative magnetic field component. Then it recover after some time. So this is called the main phase. This is the recovery phase. And whatever the minimum value of DST index we have, we assign that to to the geomagnetic storm. And this is a brief overview of the DST index, or the geomagnetic storm, that we have in the solar cycle 23, 24, and 25. And this is the geomagnetic storm that recently happened. This is the May 2024 event, and it has a DST index of minus 412 nanotesla. And there are multiple, multiple papers showing, different class of CME. We follow this paper, and here the classification are such as like moderate, intense, severe, and great storm, depending on these DST values. And if you see the DST index below minus 350 nanotesla is called the great storms. In the whole solar cycle 23, 24, and 25, there are maybe almost 4 to 5 great geomagnetic storms are there. That means the great geomagnetic storms are rare, and uh, this is this main event give us an opportunity to study this event. And because we have now multiple spacecraft, PSP Solar Orbiter, and let's say ACE, Wind, and Stereo, so on, because Stereo is also at that time, this May event is near close to the source spacecraft. So we get a better opportunity to study this storm. And the idea here is that the intense storms, if you see the intense geomagnetic storm caused by successive interacting CMEs, and there are lots of review paper and paper also like to show that the interaction of CMEs can increase their geophaticness, and so that it will also help to understand the interaction of CMEs, what is happening before and what is happening after this interaction of the CMEs. So here we pose 2 questions: that how do the thermodynamics evolve for the successive CMEs, and what is the thermal behavior in situ measurements of those protected structures at 1 AU or at high heights. For these structures, like because PSP and solar orbiter are at a different path, a different radial longitudinal heights compared to the CME direction. So for these CMEs, we only used the spacecraft like Stereo, SOHO, and Wind spacecraft. And this geomagnetic storm happened 10th May 2024, and this is the active region that generate almost in 8 to 9 May, generate almost multiple flares and CMEs. And we applied GIS model to almost 9 to 10 CMEs, try to find out what is the arrival time and what is the direction of the CME, longitude, latitude to the CME, so that we can isolate which CMEs can cause those geomagnetic storms. And we try to find out, and again we after putting all those constraints, we find out almost 6 CMEs that are responsible for this geomagnetic storm. So out of the 6, the 4 CMEs are associated with the flare eruptions, and 1 CME, that is the CME3, that happened in another active region because of some flare eruptions. These are the 3D kinematics of the CMEs. This is the leading edge speed and this is the leading edge acceleration. If you can see, all the CMEs are very fast, and if you consider these table, if you see, so each successive CMEs, like say CME2, CME4, CME6, they have a higher speed compared to the preceding one. So there is a higher chance that those CMEs will catch up the preceding CME, and there will be an interaction among the 2 CMEs. And then after getting the 3D kinematics from the GCS model, we extrapolated those kinematics up to 1 AU using simple, the equation of motion, because we know the arrival time, we know the initial speed of the CME, that is the 3D speed that we derived from the GCS model. So we try to find out what is the acceleration, and from there we imposes 2 acceleration. One is the constant acceleration, that 0 acceleration, and another deceleration that we derived using this equation of motion, so that we can get a range of kinematics for each CME and try to find out if there is a probability of interaction or not. And we find out that the CME1, CME2, so there is a chance of interaction at 40 solar radii, and CME3, CME4 at 50 solar radii, CME5 and CME6 at 130 solar radii. And because these are the fast interactions that we found out, but after the interaction, the kinematics obviously will change. That will not uh, not follow our this simple kinematics or something. So we thought that there is a probable interaction of all the CMEs before reaching at 1A. These are the again, because we try to find we derive the 3D kinematics, then we can apply the polytropic try to find out the polytropic index from the FRIS model. So this is the polytropic index for all the fast CMEs, and we see that initially, so at initial height, almost let's say 8 to 9 solar radii, most of the CME shows a heat release state, except the CME2 and the CME2. Yes, this green color one, light green color one, it shows a constant polytropic index from near the sun up to 5 solar radii up to 20 solar radii or 22 solar radii. But all the CMEs shows a heat release state initially, and there is a transition from heat release to heat injection state that we found initially for all our fast CMEs. And then again, they maintain a constant polytropic index or near isothermal state 1.1, 1.2 solar to polytropic index at higher heights. And we found that for only the CME4 at higher heights, if you see the cyan color one, it shows a deviation from this near isothermal state. It again come back to this near adiabatic state. This is because this increasing trend in this adiabatic index, we try to connect to the kinematics of the CME. Here you find that the CME4 shows a decreasing trend in the leading edge acceleration profile. So that we found that because the CME ultimately, because before that the CME is started gaining heat in those heights. So that means the CME now has enough heating. But if the CME is not expanding much, so that means the extra amount of heat will try to release. So that we saw there is a release of heat at higher heights for the CME4. Then what we did that we did the in situ measurements that at wind spacecraft. So when the CME erupted and propagated in the interplanetary space, it come across a spacecraft. The spacecraft sample a one-dimensional cut of the CME and try to find out the plasma parameters. And these are the in situ measurement for this event. And this is, you can see this is a very complex event that almost 6 magnetic ejecta come and interact and form this interacted combined structure. And if you can see this is the magnetic field, this is the total magnetic field, and this is the magnetic field component. If you see, we found one C3 region, that is the first region that we found out. Then there is followed by magnetic ejecta 1, magnetic ejecta 2. Then in between magnetic ejecta 1 and 3, that is interaction region. And similarly, magnetic ejecta 4 and magnetic ejecta 5, there is interaction region, and magnetic ejecta 5 and 6, there is interaction region. And these dotted regions that you saw here in between the magnetic ejecta 2 and interaction region, we try to find out, this is a very interesting structure that we identified that here we found a double flux rope type structure that, in general CMEs, if you maybe saw this one, this this theta. So here, in general, the CMEs, try to rotate once because the CMEs are magnetic, because the CME is the flux rope of the CME. Once a CME, once a spacecraft cut the CME, you will try to find out these magnetic field components rotate once, like from maybe positive to 0. But here for this CME2, if you see here the green one, let's say the BG component, it come from positive to negative side, again from negative to it come to positive side. So that is a double flux rope type signature. For the CME2 and the CME4, we found a similar kind of signature. So we attributed maybe this flux rope itself during the birth itself, they have a double flux rope type structure, or it could be formed because of the interaction between this magnetic ejecta 2 and magnetic ejecta 3, or similarly magnetic ejecta 4 and magnetic ejecta 5. Then these are
Soumyaranjan, I
yes,
just
yeah.
want to ask, what are these criteria to identify the interaction regions that you identify as IR1, IR2? Means you use plasma beta or the rotation in magnetic field? What was your primary criteria?
Yeah, so in general, like if this is a simple isolated CME, then you can see, let's say, magnetic field structures and plasma parameter, temperature, everything. But because this is a very complex structure, we mainly prioritize, the magnetic field rotation or magnetic field strength in that area. And once we like isolate it, yeah, in this region, the magnetic fields are, it's there is not a smooth rotation of magnetic field lines. If you see any magnetic ejector, there is a smooth rotation of magnetic field lines. But in the interaction region, the rotation is not that much. There is a simple, you can say, uh, arbitrary motion of the magnetic field lines. So these are not a simple rotation or some kind of pattern is not there. Then again, we try to find out the temperature profile. Let's say if you see any of the gray region here or here, the temperature is elevated and maybe the density is also elevated. The plasma beta is also elevated in that region. So it's a combination of magnetic field vectors and all those plasma properties.
Okay, thank
So
you.
we gave main priority to magnetic ejecta. If in between two magnetic ejecta we didn't find out any rotation or any signature of magnetic field rotation, then we assigned this as the magnetic interaction region structures. Again, these are like the speed profile, and this is the density, the proton density, this is the proton temperature, this is the electron density, electron temperature, and this is the plasma beta. And these all are from the wind spacecraft. And if you see like the speed of the CME, the whole magnetic ejecta structure, that is almost constant. This is unusual in the sense that this for obviously for this is a combined interacted structure. But for the CME, in general, the speed of the CME decreases because the CME is expanding, so that the leading edge speed will be higher compared to the trailing edge speed. So there is a decrease. There should be a decrease in trend, but for these combined magnetic ejector structure, we found the speed of the CME is almost constant up to this CME5, and for the CME5 again it increases. So it shows that the trailing structure, if you see the solar wind structure, also very high speed. So that means these CME6 also, if you see the 3D kinematics, it is also very high compared to the preceding CME. That means the CME structure, the following CME structures are now pushing the preceding structures and try to compress the IHED structures. And if you see also, if maybe this first one, so each magnetic ejecta in general the CME persist maybe, let's say, 8 hour, 10 hour, or 11 hour, or maybe 1 day, 2 days. But for all those CMEs, they are, if you see very complex structures, that means the duration of the CME almost maybe 6 hour, 4 hour, 3 hours, in that range. So it shows that the interaction of the CME, the high compressed nature of all the interactions, and yeah. So now then we try to also find out the thermal state of the electrons proton, because we have wind observation there. So we try to find out the exact polytropic index value and for the ions and for the electrons. And for the electrons, we found out if you see the first panel. So here, this again the same color bar that we found out for each magnetic ejecta. So here, if you see from here to here, there is a color things. So all the polytropic index value are above the adiabatic index value. The blue one is adiabatic index. So that means there is a release of heat at 1 AU for all the electrons. And but for the post ICME condition, if you see this solar wind, this shows a heat release state. That means there is a cooling happening. And for the pre-ICME region, there is a heating happening. So it shows a very distinct structure. So that means that the combined structure is merged with, or you can say sandwiched between solar wind structure that is heating, the IHED structure is heating, and the behind structure is releasing heat. But for the iron case, we find out, yes, Kalpesh.
Interrupt you. But as I observe here, there are multiple data points here. So you measure this polytropic index for particular time window, or
Yes, yes, yes. Yeah. So here we define a small window. Like I think for this event, we chose some 5 to 6 or 7 minute window. So it's like five data points. So within that range, I think maybe 9 minutes or something. So within that data range for six points, we try to find out one polytropic index value so that we can know the variation of polytropic index within that CME structure. So we didn't
and
assign the whole.
okay.
Mhm,
And during this polytropic index, as per I know, for the protons,
mhm,
there is one assumption that the in situ, specifically in situ measurement, the all the measurement should be corresponds to the same streamline, plasma streamline. And so to identify whether there is a streamline, mixed streamline or anything, there are certain
mhm,
filters that people generally use. For people may use Bernoulli criteria, or people may use some
mhm,
error estimation, that is dn by n, and if something is greater than that, then they just neglect that whole window. So have you used
mhm.
anything like
Yeah,
Bernoulli criterion and any window there?
for that also, I think Leverdatus or Nicholas, they use those criteria. But here we didn't use that criteria because if you just just apply some logic, like because there they used the solar wind, because the solar wind have a different streamlines, so different plasma is coming from different streamline. So let's say we sample plasma, two different streamline plasma, but here in my case, I applied something called, the correlation coefficient, because ultimately we are fitting that equation, right? Just a linear equation, and try to know the slope, and from the slope we try to find out the polytropic index value, the temperature and density. So if the fitting is good, that means the correlation is, if it is good, that means in those regions, the temperature and density are well correlated. So that means irrespective of different plasma, now my correlation coefficient will ensure that whatever the thermal state, it is well representing maybe two different streamline or three different streamline plasma. So if you apply this Bernoulli integral and all, obviously you will try to find out one streamline, like try to differentiate different two streamline. But again, it will reduce your data point for this thermodynamic measurement, and there is no correlation of no in no you can say uh, 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 or a relation between Bernoulli integral or different streamline plasma or thermodynamics things.
And,
Because if
and
even if two different streamline have different even if the plasma has window has a different streamline, if you get a better correlation coefficient, then whatever the uh, polytrophy index we are getting, that means it is well representing those two streamlines, right? So
And I
so
just observe here there is a drop across at a polytropic index of 1 in particularly proton measurement. And that we also face that, because if you use that correlation, correlation something
mhm.
like coefficient, it will just neglect all these isothermal value. And is it due to that or any different thing? I just want to ask. If you see here for the proton measurement, you will observe that at uh, polytropic index is equal to 1 there, you will not hardly
Yeah,
observe
there is
anything.
nothing.
Yeah,
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 yeah, yeah.
yeah.
Yeah, initially I also thought like why there is not even a single data point at one.
Because that
So
is correlation dependency. If you see there, the
yeah, yeah,
correlation just wash out everything around polytropic index equal to 1.
yeah,
Yeah.
yeah.
Sorry, I
That
will
is
not take further
yeah,
of your time.
yeah. It's just because of that, and but even if that also, we also remove that correlation coefficient, but uh, we get a similar kind here also. Like if you see the proton polytrophic index, we get a bimodal type of distribution, that there is one distribution above, let's say, one value, and there is another type of distribution below this one value. So here, this bimodal distribution also persists. If you see in my plot, like I have plotted two things. One is the orange one, and the background one is the gray one is the like less correlation coefficient one. Even if we include that, we get similar bimodal type of distribution. So there are some points at one, but again it maintain a bimodal distribution. But and for the proton case, we found a mixed thermal state that in the combined structure we found a mean value of 1.31. So again, it shows a dominant heating state, but we again see local heating and local cooling for the protons. And the proton again is sandwiched in between two similar kind of solar wind, that the pre-ICM solar wind is also heating state, and the post-ICM solar wind also shows uh, uh, a heating state. And here also we found out those uh, the double flux rope type structure we found out. So in literature, people find out if in the double flux rope, the two flux rope, the flux tube, have two different kind of polytropic index. Here, if you see this electron polytropic index, so this is a magnetic ejecta 2. Here, the polytropic index value for this dotted region and this region is different. And here also this pink color one. So here the polytropic index, and here you can see a clear variation in polytropic index in between this and this and this and this. So this shows a clear signature of a double flux rope type structure. And from here also we conclude, confirm and conclude that these are two double flux rope type structure that may be formed because of the interaction, or maybe they formed during their eruption itself. And here also interesting. Yes.
Uh, you have defined something heating and cooling for electron and proton plots. How you decide whether
Mhm.
there is a heating or cooling on the basis of polytropic index? That is first question. Second question was, in earlier FRIS model, most of the data point was showing that your all CMEs are nearly isothermal. But over here, we are observing isothermal is clearly observed, rather than that it is close to adiabatic domain. Why?
Yes. So here, so in my Priest model, so this is like a single fluid model, right? So here we consider both the electron and proton contribution, and here the temperature was like sum of the average temperature of electron and proton. So if you, let's say, sum the electron polytropic index and this ion polytropic index value, you will get a similar kind of value like 1.1 or 1.2 or 1.3 values. But here, because we now isolated two values, so the in my paper also we tried to connect this in situ measurement measured polytropic index value to the FRIS model derived polytropic index value. But it's not a one-to-one correspondence, because here the polytropic index in the FRIS model, the polytropic index was, you can say, the average of the proton and electron values, because here inherently we took a single fluid model. And here we try to find out for electron separately and for ion separately. Here also we try to find out the effective polytropic index, giving the weightage to temperature and pressure. And here the values also comes around 1.1, 1.3, 1. Maybe 4 or something.
But
But obviously this is a very
sorry to disturb you, but it look like to be the mean value is goes towards 2.78, and for proton it is 1.31. So if we even though find out average as per your argument, it goes into something like adiabatic or something higher than that. Whereas
yes. If
highly
you
dominant isothermal.
yes, yeah,
I was
because
little bit confused about this, means why we are getting two different things.
No, I think, this, whatever the measurement you are doing, this is at 1 AU, right? And
Yeah.
whatever the FRIS model derived point I'm showing, the last height is also around 25 solar radii or 20 solar radii.
Yeah, but
So
then it
this,
should be, means I read about couple of papers of Vagish also, who suggest that it is
Mhm.
at the adiabatic initially or super adiabatic initially, and then it moves to isothermal. So as we move close
Yeah.
to 1 AU, we should observe more dominant isothermal as compared to adiabatic or super adiabatic. But here the case is opposite. Look like to be
Yes,
opposite.
yes,
That is
yes, yes. Yeah, yeah.
isothermal close to the sun and adiabatic or sorry, non isothermal at 1 AU.
Yeah,
With
so these are like for whatever he said, like in this paper, like initially there is heat release state, then again it maintain isothermal state even at the 1 AU, but these are
yeah.
for single event CME, like CV11 CME. There is not much interacted
But
CME. But
okay,
here the
no,
CMEs are interacted, right? So that's why,
yeah,
like, even if you see, like, in general, the CME, the electron temperature is, you can say, is high compared to the proton temperature, right? In CME
right.
cases. But
Hmm.
for this combined structure, the electron temperature is lower compared to the ion temperature. So everything will change when the CME is interacted, right? So here,
Okay,
that's why only you can see a very different picture here. But for if you individual CME you see, you'll see the temperature, the polytropic index around that value only 1.1, 1.2, near isothermal, like
okay,
not adiabatic or so. But because of the interaction only, here the profile changes drastically.
okay. And how you decided heating and cooling on basis of what?
Yeah, heating and cooling, just if you see the derivation, in the theoretical derivation of the polytropic index, if the polytropic index value is less than the adiabatic index value, that is 5 by 3, that means there is a heating state. Heating means the dq by dt is positive, the heating rate is positive. If the value is above 5 by 3 value, that means there is a release of heat. The dq by dt is negative. The change in heat is negative. So that means the final heat is less than the initial heat. So
Okay,
depending on the threshold value is the 5 by 3 value. If below this, then that is a heating. Above this means that is a release of heat. But we use this in a loose statement that release of heat. If the CMEs, let's say, have a polytropic index value above 5 by 3, it may be natural because the CME is expanding and propagating. So naturally, the heat content of the CME will decrease, right? So it may not be release heat. It may be, you can say, the decrease in heat. But
okay,
for the heating case, obviously there is something that is adding heat into the CME, maybe from the background solar wind, or maybe inside the CME some process is going
okay.
on. Yeah, yeah. So yeah, I think this is the last slide. These are some take-home points. Uh, so that we find out that the CMEs are not propagating adiabatically. That many people put constraint in the MSD models that polytrophic index value of 5 by 3. Here we found out the CMEs undergo multiple heat transfer during their interplanetary journey, and during by doing the DM analysis near the sun, we found that the electrons probably saw heat release state, and using white light observation and our FRIS model, we saw that the CME shows a heat release state near the sun, means maybe or at most around 2 to 5 solar radii, and then followed up by a near isothermal state at higher heights, up to around 25 solar radii. And the in situ measurements, like we did for various CMEs, like for fast CMEs, slow CMEs, and we found out it's maintained near isothermal state even at 1 AU. But for specifically this 10th May 2024 event, we found out the proton shows a mixed thermal state with a dominant heating signature, a local heating signature, and also so heat release state. And for the electron shows a heat release state, a dominant heat release state for the combined structures. And we found out that electrons can be a better proxy for the recent CME interaction because the electrons have a less mass, so they have a higher mobility. So any disturbance in the thermal state, temperature, so they can react more quickly. So if there is interaction happening, so that's why you can see the electron polytropic index, because the CMEs are already interacted. So that's why you see now the CMEs are releasing heat. So that's why it's so a heat release state. And if you even see the overall trend of the polytropic index, so it is slowly increasing. So that means higher value of polytropic index above 5 by 3 means it's releasing more and more heat. So more heat releasing means these latter structures are interacted very recently compared to these earlier structures. So we found out that those signatures you can find out from the electron thermal state about the CME interactions. And I'll end with this. This is a beautiful picture of the 10th May event. This is the aurora that we see in the Hanle in Ladakh. And this is the Himalayan Chandra telescope that is operated by Indian Institute of Astrophysics, our institute. And this is the background Milky Way. So yeah, that's it. Thank you for your attention.
Thank you so much, Soumyaranjan, for this really informative talk. You have beautifully derived the relationship among the fast and slow solar CMEs and its relationship with the expansion CME interaction and how these features can be tracked in terms of the geomagnetic storm. So thank you so much again. So I would like to ask to the audience if you have any question still, so you can free to ask to our speaker. Is there any question from the audience?
Yeah, I have a small question. Yeah, Devesh here. Yeah, Shoumu is a very nice talk. So I just want to ask you, so is that how the gamma polytropic index can be or should it be correlated with the storm index? Like, shall we expect that it should be correlated with the storm index or not? Like,
No,
not.
I
Okay, yeah.
I just recently in one of my paper I try to find out that correlation, but it's not there is not any correlation like DST to a polytropic index value, because ultimately the DST whatever the geomatic strength that you are talking about, it's maybe I'm feeling maybe combination of everything, like magnetic field strength, the plasma temperature, everything. So it's not like if the CME is, let's say, heating state, it will cause more geomatic storm than a CME causing a heat release state, something like that. So there is no correlation.
There is no correlation. I think it should be expected either, because polytropic state is basically the internal state, and it usually relates with the expansion or something to do with the like gas pressure, something to do with this. But DST is basically measured with the BZ, right? The strength of the BZ. So
Yeah,
I think
maybe a combination of, let's say, the magnitude of BG or temperature and polytrophic index, a combination of something can be related to DXT, not a single function of
not a
polytrophic index to
single.
DXT. Yeah.
Not a single thing. And another question I have is that, do the gamma actually also related with the CMA speed? Because you just showed using the FRIS model that like from a fast CME and from the slow CME, we get the
Yeah.
similar kind of gamma, like close to like far from the sun, like it's almost like isothermal. So means that it is almost independent of the like speed of the CME. Am I right in a sense?
Yeah, like it is in my one of my paper also, I try to find out the kinematic relation, thermodynamic and kinematic relation of the CME. So there is not you can say a quantitative relation between the CME speed and the polytrophic index, because maybe the CME yeah, there is no direct relation, but we try to find out the rate of change of speed, because maybe whatever the speed it has, it may be inherently it has some speed because of some process, because of some forces while it's eruption. But the internal plasma, how it evolves, all depend on the expansion speed rather than the propagation speed, right? Because whatever, let's say, the temperature increase or pressure is increase, it will directly impact to the expansion speed, not the propagation speed. And also that it will change the acceleration of the CME, like the expansion acceleration of the CME, not the speed directly. So if there is change in acceleration, so we try to find out the the acceleration to the the polytropic index. Again, we didn't find a good correlation, but still there is some correlation. Like it's not correlation not coefficient not above, I think 8, but it's around, I think,
+8, right? Is it like
0.6, yeah, +8, yeah,
+8?
it's something, I
Okay.
think +6 or something.
Okay.
But there is some relation that we found, that those because ultimately we found out all of our CMEs that now transition into heat release to heat injection state. So we
Mhm.
try to find out if the CME speed is higher, so maybe the transition height will be vary, maybe near close to the sun, or away from the sun. So there is a good correlation that
Mhm.
if the CME is expanding too much, so it will uh, uh, it will quickly try to find out. It will try to quickly get into isothermal state, and also if it's a very fast CME in comparison to fast and slow CME, if a very fast CME, then it will try to get to the isothermal state very quickly compared to the slow CME.
Okay. Nice. Thanks, Shobhan. Thanks. Yeah.
I think
Yeah.
there is Dinesh who wanted to ask question to the speaker.
Yeah. Hi.
Over to you.
Hi, Soumyaranjan. It was a nice talk.
Yeah.
And
Yeah.
I missed the initial part, I think. So sorry for that, but I'll just ask a quick question. So, what exactly is the input for your FRIS model from the GCS or the chronographic data?
You mean like the input for my FRIS model?
Yeah, I mean from the data, like the height and what
Yeah.
else? Or
Yeah,
or
for
does it?
me, like, yeah, I need the complete kinematic profile, like, let's say height. So the first one is height, then again try to find out the speed and acceleration of the CME. So these are like free, and again the derivative of acceleration. So these 4 things I need: height, speed,
Uh,
acceleration, and derivative of acceleration.
Okay, if that is the case, then how sensitive is your model for these values, considering the uncertainties in the GCS and
Yes, yes,
yeah.
yeah. So if you
Sorry if I missed the initial part.
no, like, so if you see, so yeah, you may not be notice here. Uh, yeah, so can you see my screen now?
Yes, yes.
Like this first semi. So here what we did, that again, like this is model, whatever
Yeah,
the height you
yeah.
choose, this is your best height, right? So here
Okay.
what we did, that we give a error in our model, that we give a
Okay.
10% error. Suppose if you see this height, we give a 10% error in our height measurement. Again, we translate into our speed. Again, we translate into our acceleration. That means now these are the error for my kinematics. So with that error, uh, if you see in the polytropic index, the error, I also plotted here the error, but the error was very less. That means there is
Oh,
not
okay.
very much effect in the polytropic index, but obviously in temperature and in pressure, they have more uncertainty.
Pronounced.
But in polytropic index, the uncertainty is very less. So
Oh,
that's why,
okay.
like in my recent paper, I try to not to plot this error bar here, because the error bar is very less for polytropic index at least. But for temperature and pressure, there are some error bar, like maybe 10% or something.
Okay, okay. And this 10% is just a random choice or just a
Here, yeah, because we did, because these are no manual fitting, no. So this is model. So what I did, that we randomly did in our group, like just one person do some this is fitting, again I will do this is fitting. Then we'll see like how much it is varying. So depending on that value, we choose, it is varying 4%, 3%, 5%. We just give a highest value, like maximum 10%.
okay.
Yeah.
Thank you.
Okay, thank you so much. Anyone have a question to the speaker? Okay, if no, then I would like to thank again to the speaker. Before we leave, I have a general question to Soumya. Soumya, you showed the relationship of the fast CME with the heating using the differential emission measure analysis.
Yeah.
And yeah, so just wanted, I was just curious to know, like because you have selected a few cases in which you found the heating for all the fast solar for all the fast CMEs. Um, uh, what will you say in the generalized way? Because you in few cases it is heating, but what if we are looking onto the broader picture for all the past CMEs? Other question is like, is there any relationship with the gradual increase in the X-ray flux during the flare? Because during the impulsive phase, we can say that the CME which has been erupted must be fast, and maybe the heating might be prominent. But if the flare gradually evolve, so in that case, there should be heating, but I'm not sure at the moment. So what do you suggest?
Yeah, I think the first one, like for the general case, again, whatever the CME we choose, so these are only based on their kinematics, because we try to find out for which CME we can try to find out the best kinematics possible. It's not, related to any, the selection is not related to anything like to the source region or something like that. So
All
we
right.
solely based on that, whatever the CME for which we can try to find out the kinematics. So that we see the chronographic field of view, which CME is the best picture, then we choose that CME. So overall, like let's say almost maybe 10, 12 CMEs till now we did for the first CME case, we did. So for all the first CMEs, we see like initial heat release state, then followed by a heat injection state from the FRIS model. And initially this was all heat release state. So that means they have more heat, right? So that's why they are releasing heat, and more heat means more temperature. So we suspect that all the fast CMEs have uh, more heat. But for recently, let's say uh, for this geomagnetic storm, one CME holds like a heating state near close to the sun itself. So maybe a dedicated case study, like where this, connection to the flare, gradual flare or eruptive flare or
Yeah,
something like
that's what I
impulsive
was
flare.
asking.
Yeah,
Yeah, thank
maybe a detailed case study may be developed, because if you see here, maybe CME2, the CME2 here close to the sun itself, it is showing a polytropic index, around this value, but all other CME shows a heat release state. So
uh-huh.
maybe a detailed study why this CME shows a heating state even close to the sun will give some general idea, like two
Uh,
different class of CME or different class of flare or something like that.
Yeah, now I get it. I mean, you have selected the cases based on the speeds. We are not looking onto the
Yeah,
near
yeah,
sun dynamics, basically. So we are
yeah, yeah.
just
We
looking
just
onto the interplanetary thing, right? Yeah.
yeah.
Okay, thank you so much. And if you still have any question in audience, you are free to ask before we close this session.
The
I
first
think,
CMEs are, hello, sir.
yeah, please.
First, the soul of CME catalog, first CMEs are mostly decelerated, but some first CMEs are accelerated. How these fast CMEs are getting accelerated? At that conditions, what happens to the thermal conditions for these fast CMEs?
Yeah, like it will, like the fast CMEs will not no accelerate in the sense like it will not accelerate that much, like to the initial heights. Let's say these CMEs, so these are, you can see all are fast CMEs. So there is a decrease in acceleration profile, and here they change to a negative the acceleration. So a negative acceleration means the CME is decelerating, right? Like sorry,
Yes.
if a negative acceleration means now the CME speed is decreasing, but still is not decreasing as before, right?
Yes,
So
but
ultimately, yeah, tell.
some CMEs are having a positive accelerations.
So ultimately, like if you see here, like all the CMEs are now trying to get into a zero acceleration state, right? So here acceleration like is almost zero. So all are trying to connect to that state. Obviously, in a local scale, you'll see some variation because some sort of uncertainty because we try to find out the height, then again do a differentiation, then we find out the speed, and again differentiation we try to find out the acceleration. So there will be some sort of uncertainty. But if you see the global picture, all the CMEs are trying to go close to this acceleration value zero. That means a constant acceleration value they are attending.
Okay. And if it has constant accelerations, then what about its thermal conditions? It is adiabatic or isothermal?
So if they're attending a constant acceleration, so in general we found they are a near isothermal state. So if you see the polytropic index value here, so for all the CME in their gradual acceleration phase, so they are now maintaining a isothermal state, right? So if you see this red patch, so here all the CMEs now in this zone, that means a near isothermal state, maybe 0.1, 0.9 or 0.1.1 or 1.2, something like that. But again, this small variation will reflect a big variation in the temperature profile. Like, the drop is, for some CME, the drop is very high. For some CME, the drop is very less. Something like that. But there is not a one-to-one correspondence quantitatively between if the CME is very fast, then maybe the drop will be different or something like that.
Suppose if it is accelerated means the temperature increases, isn't it?
No. Like we didn't find any relation like that. Like if the CME is accelerated, means the temperature will increase or decrease, something like that. We didn't find any relation there.
Yes.
Okay, now let us thank to the speaker for this really interactive session for this inter-seminar. And if you still have questions, you can directly communicate with Soumyaranjan for the further discussions. And okay, thank you for the audience to join this in the seminar, and I will see you all probably in the next seminar. You will get the notification out of it. Thank you so much again, Soumya, for this talk here in the Indus seminar series. Thank you. Thank you, everyone.
Thank you.
Good night.
Thank you.